I think another hand has been raised. Oh, there's no hands here. There are no hands raised there. Okay, so I think there are no hands raised here. So we can move on. Okay, so we want to solve this question. A box contains 6 white balls and 4 red balls. If we randomly draw two balls from the box without replacement, what is the probability that the second ball selected is red, given that the first ball selected is white? Then B, what is the probability that both balls are selected are red? So I'll leave you to attempt this one. Thank you, my people. My people, let's mute ourselves. So otherwise, your voice intermittently comes, and we could hear whatever that is happening at your end. You may want to hide your privacy at that time. So let's continue. Let's look at the first one. So to solve this, we use what we call the tree diagram. The tree diagram. So here's the tree diagram here. For the tree diagram, the probability that we have probability of red or probability of white in the first instance, the first draw, we have 6 on 10, and probability of red, we have 4 on 10 here. So probability that we will have white, we have 5 on 9, and the probability that we will have red, given that white has already been drawn, we have it as 4 on 9. So probability that we have white, given that red has already been drawn, 6 on 9. Probability that we have red, given that red has already been drawn, is 3 on 9. So in this instance, using the tree diagram, we can continue. So since we are interested in the probability that the second ball is red, given that the first ball selected is white, we can simply look at the tree diagram. That is the probability of red, given that white has been selected, which is 4 on 9. That will be the answer we are after. But then we have the formal way if we are supposed to use the formal way. And the formal way is this. We have probability of red intersection white. And red intersection white is the same as probability of red times probability of white, because probability of red is an independent event from the probability of white. So just multiply. So that will be divided by probability of white. And this, we will say this one will cancel out this. And we have the answers 4 or 9. You could also use the tree diagram to get the probability of red, given that white has already been drawn, which is from here. You can get the 4 or 9. I don't know if you get it. So you can either use the formal way or use the tree diagram. And the second question asks that someone has raised his hand. Joshua.
Yes, sir. Please, I want to ask the question.
Joshua, you can ask your question.
Please, what if you won't use the tree diagram and the formal one? Because this one, a box containing 6 white balls and 4 red balls. The probability that the second ball is red, given that the first ball is white. You know that the first ball is white will be 6 on 10, which means the second ball, if it will be red, it will be 4 on 9. Like not drawing the tree diagram or not using the formal or the formula. Can you do that?
You can do that, but you see, in exams, marks will be awarded. This I hope you understand. And when we are awarding the marks, we mostly award M1, A1. M1 means method, and A means accuracy of your answer. So the method that you use. Here, you've used the method in your mind, which was not clearly shown here. Please, I hope you understand. If you write just 4 or 9 for us, though you are correct, you have the accurate answer. But which method did you use? And accuracy cannot be given when there is no method.
Oh, okay.
Please, I
Thank
hope
you
you.
very much.
So, what your intuition is very great, just that because this is more of a formalized something, you would need to see what you've done.
Okay. Thank you.
So, so the second one we are on is we want to find the probability that both balls are red. Probability that both balls are red. We have P1 intersection P of R1 intersection P of R2. This I hope you understand. So this means the probability of red and red is quite different from probability of red, given that red has already occurred. That is the second chance for drawing red. This I hope you understand. So this means the probability of R1 being red, the probability of R2, the probability of the first ball being red, and the probability of the second ball being red. So that means probability of R1 and probability of R2, given that R1 has already occurred. So this is just for the second draw. This one is just for the second draw, while this is for the first draw. So we have it as 4 on 10 times 3 on 9. And the answer is 215. 4 times 3 9. And the answer is 315. Or you can alternatively use the combination approach. Right, the combination approach looks at without replacement. Without replacement. In the instance that we have with replacement, the combination approach does not suffice. So here we are looking at with replacement. So without replacement, the condition you can use the combination approach, but with replacement, the condition and the combination approach is not the best to use. So we have 4 combination 2 times 6 combination 0. The 4 combination 2 is we have 4 red balls. So 4, and you want to select 2 of them. We have the 4 combination 2 times. We have 6 white balls, but we are selecting none of them. That's why we are at 0 times. In total, we have 10 red and 10 balls, and you want to select 2. That's why we have the denominator here. And that gives us this answer. Please, I hope we get it. So I'll give time for you to look at the second question. Let's look at the second question. Let me give you 5 minutes to work on it. 5 minutes. Okay, we have 2 minutes more. We are attempting this question. We have 2 minutes more. Okay, your time is up. Let's see. Let's see what you got. Let's see. Anyone who had found an answer to what we just gave. Three fair coins are tossed together once, and the results were observed and recorded. Okay, let me see how many people have been able to find responses to it. Yeah. Three fair coins are tossed together once, and the results were observed and recorded. They are required to find the probability of obtaining. Yes, Kwekubuama. Yeah, Kweku, tell us what you got. If you can even show a picture or something.
Is it a final answer or the procedure?
Pardon?
Sir, is it a final answer or procedure?
Hey, you can tell us your final answer.
I got 3 on 4.
You are 3 on 4. Lucas is giving appreciation, also saying 3 on 4. Let me see those who had 3 on 4. Let's raise our hands. Yes, watching someone. Okay. I think everyone had 3 on 4. Okay. So let's see if you did it this way. Okay, someone has raised a hand. Please, whoever has raised a hand, you can talk. Someone raised a hand. I think Joshua, are you the one who wants to talk?
You said we should raise our hands. Those who are
Okay.
okay. There is what I did. So if 3 fair coins are tossed together once and the results were observed and recorded, so I recorded the results. And I had 8 sample space. I had 8 items, like head, 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 tail, tail, head, tail, 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 head, head. I got 8. And the next part is find the probability of obtaining at least 2 tails, given that the first coin falls on tail. So the probability of getting at least the event of getting 2 tails, I had 4 of the items: head, tail, 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 head, tail, then tail, tail, tail. Then the other part is given that the first coin falls on tail. The first coin falls on tail. So we are talking of if the first coin falls on tail. Oh, this one is I have to do illustration, but I don't know how to use the board. So
Okay. Oh, yeah, here. Let's see. Let's see if we had this one on the want of time. So if we were able to get this, we are tossing it 3 times. So these are the various toss here. And the question asks that we should find the probability. Find the probability that at least 2 tails of obtaining at least 2 tails, given that the first is first on a tail. So we are looking at the first falls on a tail. That's this one. These ones. So the probability of A's are that the first falls on tail. That is T, 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 and T. And the probability of getting 2 tails, we have them here. These are the probability of obtaining 2 tails, at least 2 tails. So A intersection B is giving us those that can be found in A and that can be found in B. This cannot be found there, but these can be found there. So the probability of that is 3 on 8, while the probability of A is 4 on 8. That can be found here. So the answer is 3 of 4, or 3 quarters, or 3/4. We want to move on to the multiplication rule. The multiplication rule is that the probability that 2 events, A and B, both occurs, and it is given by probability of A, sorry, probability of A intersection B is equal to probability of A times the probability of B, given A has already occurred. Same as probability of A intersection B is equal to the probability of B times probability of A, given that B has already occurred. So this is what we call as the multiplication rule. In essence, from the conditional probability, we just make the numerator the subject. And that is what the multiplication rule talks about. So let's solve questions involving the multiplication rule. 1. A box contains 6 white balls and 4 red balls. We randomly, without replacement, draw 2 balls from the box. What is the probability that the second ball is red? So yeah, the question is just telling us the probability that the second ball is red, or it's asking for the probability that the second ball is red. In essence, what we are looking for is we could obtain a white and a red. We could obtain a red and a red. So let's quickly go to our tree diagram and go to the tree diagram. The probability of a white is 6 on 10, while the probability of a red is also, is it 12 balls? Let me check. No, there is a mistake here. I think there is a mistake here. So this is supposed to be 4 on 10 or 4/10. So let me replace it with 4/10. And that 4/10 here. So this instance is 4/10, not 6/10. So in the second row, if the second ball is white, we have white given that white has already occurred, then we have red given that white has already occurred. And here we have probability of white given that red has already occurred, and probability of red given that red has already occurred. Now the question is, we should find the probability that the second ball is red. Probability that the second ball is red. That means that we could get the first instance being white whilst the second is red. Or we could get the probability that the first is red and the second is red. That leads us to this combination here. So probability of obtaining the second to be a red means that the probability that the first can be white times getting red, or getting red and then red. So when we simplify that, we have that to be plus, and this first part is equal to this. So probability of white times probability of red, given that white has already occurred, plus probability of red, given that red has already occurred. And that gives us the solution to be 2/5. But I hope we get it. I hope we get it. Hey, have I muted myself? Have I muted myself?
No.
Please say two more light. Please say two more light on that part.
Which part?
Yeah,
So that I
this
can
one.
go specifically.
Yeah, this one. The solution.
The solution. Which part of the solution, please?
The second one. After the first, the first formula, the second one equal to P of W1 intersection R2.
Okay, so this one, P1. So the first one, yeah, is essentially, that's the property of probability. We can look at the individual ones here. So, oh, where is my technology? So this can be written as probability of white intersection red. That is, you are getting a red first and then, sorry, you are getting a white first and a red second. Or you can get a red first and a white secondly. So from the multiplication rule, it says that if two events occurring, that is A intersection B, can be given to us as probability of white times probability of red, given that white has already occurred. This is because the question asks us to find that the second ball was red. And that same can be done for this instance. So ideally, we should have written P here. So the second instance here too, we have probability of red, given that red one, given that, sorry, probability of red times probability of red, and the second ball being red, given that R1 has already occurred. And these are substitutions from our tree diagram, which we had here. From the tree diagram, this is what we have. So we simply substitute. Probability of white is 6 times on 10. Probability of red 2 given white has already occurred is 4 on 9. So what we did here was to substitute. And that substitution there, and the rest becomes mathematics. Please, I hope you understand.
Yes, please.
Yes, please.
So the multiplication rule can also be extended to 3 or more events. So here, if we have 3 events, probability of A intersection B intersection C can be the probability of A. So here, if you, the intersection as an operator is associative. That is, we can look at 2 at a time and give the same answer. So if we are looking at 2 at a time in intersection B, before we look at its intersection with C, that will give us probability of C, given that A intersection B has already occurred, times probability of A intersection B. And probability of A intersection B itself can be written as probability of A, given that A times probability of B, given that A has occurred. So that's what we do. We now substitute. Since this is already equal to that, we now substitute there. And by extension, we have probability of A intersection B intersection C equal to probability of C, given that A intersection B has occurred, times probability of B, the probability of A, times probability of B, given that A has already occurred. If we are to further extend it to 4 events, we can have it as probability of A intersection B intersection C, sorry, intersection D, and that is supposed to give us probability of D. This, I'll leave you to go and prove it. Probability of D, given that A intersection B intersection C has already occurred. And we know that times it will obviously be multiplying probability of the whole of this. And this probability can be given as probability of C, given that A intersection B has occurred. And we know that probability of A intersection B will now be equal to probability of A times probability of B, given that A has occurred. So we can extend it to so many events. So let's solve a question here. Extending it to 3 events. Yeah, there won't be any proof work. You just substitute them. So 3 cards are dealt successively. It should be drawn successively at random and without replacement from a standard deck of 52 playing cards. So we know the standards for 52 playing cards. What is the probability of receiving in order a king, a queen, and a jack? And that is the solution there. We know that we can get just 4 kings, you can get just 4 queens, and you can get just 4 jacks. So probability of obtaining a king is 4 on 52. Whilst probability of obtaining how many different cards do we have in a playing card?
There are 4.
I mean, how many different cards? We have king, queen,
Yeah, we
jack.
have.
Let's say we have
And
the
then
10.
numbers.
1, 2, 3, others, the all parts.
There are 2. If your
They are all
Is it
52.
56?
The question is how many different cards? I don't think we have the card 1. We have the SA, that is the A. We have the 2, we have the 3, we have 4, we have 5, we have 6, 7, 8, 9, 10. That makes 10. Then we have the king, the queen, and the jack. That makes 13. So we have 13 different cards by 4. That gives us 52. So probability of K1, that is the first card being K, is 4 on 52 times the probability that we have a queen, given that K has already been drawn. That gives us 4 on 51 times probability of obtaining a jack, given that a queen and a king has already been drawn. That gives us 4 on 50. And by so doing, we have this formula there. This, I hope we get it.
No, sir.
Yes, please.
I think this one I didn't go by a tree diagram. I think that's why there might be some sort of. Let's go by a tree diagram, but by first let's write down this formula. Let me clean my formula. The extension, you do the extension by yourself. Extension to 4 different events. Please, you do that on your own. Please, let's put that formula there in down. Let's put it down because that's what we are going to use. So here we have 3 different events. So I hope we've put that formula down. Having done that, so probability of king, we have probability of queen, we have probability of a jack. So we know that probability of a king here, the first instance being a king, that gives us 4 on 52. And that splits us into 2. The first being probability that we have a king. So because we have 3 events, it's split into 3. Probability of a king, given that, probability of obtaining a king, given that a king has already occurred, or a king has already been drawn. We'll have this as 3 on 52, on 51. Each my writing what is happening. While this probability of getting a queen in the second draw, and this will take quite some time, given that a king has already been drawn. We'll have it as 3 on 51. So that will be what we are after. So in that order. So I'll leave the others since you are not after them. We'll move on to.
Please, the second one, I want to ask a question.
The 3 on 51.
Yeah.
Sorry, it's a
Only-
mistake. It's supposed to be 4 on 51.
Okay.
Thank you.
It's supposed to be 451. I like how you are following it. As soon as there is a mistake, I'm quickly drawn to it. Thank you. That's good. So we have the probability of obtaining a kin for the third one, given that we have both a queen and a king occurring. And that is, I think with this, that will be 3 on 50. So this is 3 on 50. So probability of getting a queen, provided that queen has already occurred, this one will be 3 on 50. And let me write what we are mainly after. Probability of a jack given that we have both a queen and a king occurring. That will give us, because this is our first selection of 4 on 50. So we multiply this, multiply that, and multiply that. So that's at succession. That's what we use here. Oh, shoot. That's what we use here. And we had that. I think there is some form of clarity here. Please, I hope you understand. Hello.
Hello, sir.
Yes,
Hi,
please.
say.
Please, I hope we get it.
Yeah, but
Sir,
I think Hannah is
sir, the only issue I have is the last one that you wrote, the Jackson.
Mm-hmm. Okay. Gifty
Why
will
didn't
come to you.
it? All
Why
right.
didn't I want
Why,
to get that
why,
one.
why didn't it come under the first three? I think it would be better if what you did already, I can see it so that.
It's cleared. What I just showed a white screen. So when I show the white screen and I get it back, I
The
unwhite it
second draw,
whatever I want to. Pardon?
the second draw that we had the jack to be 3 on 51, and then the king to be, I think, was it 2 on 51 also. Under it, you didn't bring the jacks on, but the last one that we did, the jack had 4 on 50, and I don't get it.
This is because we've not selected Jack over the period. Already we have chosen 2 balls without replacement. This I hope you
Okay,
understand.
so
So when you select,
why did we jump from the first one that we didn't select any jack there, but we jumped to the third one, the third row?
you don't, I don't get what you mean. What I did is this. The question asks that we are receiving it in order from the king to the queen to the jack. That means that in the first instance, you are supposed to select a king. This I hope you understand. So when I draw the tree diagram, I
Yes.
did for the kings first. And now I move to when we select a king, the second instance we select a queen. When you select
All
a
right.
crane, that's where we had the 451, where most of us corrected me. So when the 451, that is the instance where you selected the crane. I didn't move on to a cane and a cane. I
All
didn't
right.
move on to a cane and a jack. So from a cane and a crane, I now move on to the crane. From crane, we are now supposed to select a jack. So I didn't move to a jack and a crane and a cane. I didn't move on to a crane and a crane. I just move on to a crane and a jack. So that
Oh,
succession will have 4 on 52, 4 on 51, and then 4 on 50. Why is it 4 on 50? Because we've never selected a jack. We still had 4 jack cards intact. And why is it on 50? Because already we have selected a king and a queen who are 2. So when select 2 out of 52, you have 50. So the total number of cards in the third selection or the third chance of selecting will be 50. And the total number of jacks in there will still be 4. That is why we have it as 4 on 50.
all right, sir. Thank you.
You're welcome. Kwaku, please, you have raised your hand.
Sir, now I want clarification on the formula. Probability of A that in B is C. That is the
Kwaku, it seems your voice is a little bit far away from the phone, making it a little difficult to hear you.
okay. Let me.
Yeah, it's a bit clear now. Oh, it's off.
Hello,
Yeah,
can you
Kwaku,
hear
you
me
are
now?
back. Yeah,
Yeah,
we can hear
I
you.
I said looking at the formula, probability of A intersection B intersection C, as we have do and then undo in mathematics. Is it in that succession that probability of C, given that A and B has already occurred, and then when it comes to A and B, it should be B, given that A has already occurred, because B and A and B we can have probability of B, given that A has occurred.
Yes, and those two probabilities will still amount to probability of A and B. Please, I hope you understand.
Yeah, probability of A and B, and then we will do it in the way that is written. That is probability of B, given that A has occurred.
Let me go to the page so that the others can appreciate what we are talking about. This is where you are having the question, right?
Yeah. I just want to know if it is always in that succession from the last followed to the second and then to the first.
That is to allow us understand it. But no, it since intersection as a rule is associative. Someone can intend to substitute, to change the order. But that is for us to understand it. That's why we made this successive.
Okay. Okay.
Please, I hope you understand. So
Yeah.
the part where we grouped it, someone could have started from A intersection C, intersection B. Then you have that there. There's an
Uh,
organism appearing there.
okay. So
Just
whichever way you go is accepted.
is accepted.
All right.
Once
Thank you.
it makes sense there.
Okay. Thank you.
You're welcome. Okay. Just as we said, we are going to apply the question to our real world. Let me give you 5 minutes to apply the question to our real world context. For application one, I would give that to you in 5 minutes. Please, we have 4 minutes more. Okay, so our time is up. Let's see if you obtain a solution as this. Let's see by hand those who had a solution like this. Did we have a solution like this? Anyone?
Only the first one, but the second one I had it wrong.
Anyone else? So the question reads that a company has 300 sales representatives. During the past year, 48 of the sales representatives earned a bonus by selling over their quota. At the beginning of the sales year, the company offered a special training seminar which was attended by 138 of the sales representatives. 27 of the sales representatives who earned a bonus and attended the training seminar. So you see the conditional probability there. What's the probability that the person who attended the seminar earned a bonus? So first, once we have 138 attending the seminar, that means we have 162 not attending the seminar. These are all we get it. So that is where we had the A, this one coming from. And the question reads that we had out of those who selected, that's where the B comes in. The B comes in that we have 48 people who attended it, who attended or who earned a bonus. So the 48 who earned a bonus. In the question, we have 27 of the sales representatives who earned the bonus attending the training. That tells you that there are 27 of them who attended the training. That gives us the 27 on 138. And if 27 of them attended the training, that means 21 of them did not attend the training. So from here, we can easily pick this as those who as the answer for the A. That is the probability that the person who attended the seminar earned a bonus. So that is that. Or you can use the former approach, where the former approach is probability of A and probability of B occurring. This I hope you understand. Probability of A and probability of B occurring. So that would have given us probability of B, given that A had already occurred. And that is equal to probability of A times probability of B. All on probability of A. I know probability of A is 138 on 300, and probability of B is that we have it as 27 on 138. So probability of B refers to the event that someone earning a bonus, and we have 27 of them who attended it and the bonus, given us the 27 on 138. So A will cancel out, and we have the probability of, so given us 27 on 138. Now probability of A and B. So looking for probability of A and B, which is to find if a sales representative is selected at random, what is the probability that the person attended the seminar and earned a bonus? So probability of A is you attending the seminar, and then you, that same person, attending or receiving a bonus. So we have the probability of A, which is 138 on 300 times you attending that seminar and receiving the bonus, 27 on 138. So you have it as the 27 on 100 on 300, because 138 will cancel out. And then you have it as 9 on 100, given as 0.09. This, I hope we get it. So we will end with this trial question here. And then in our next meeting, we will look at the Bayes theorem. Please, do we agree that we can meet on Wednesday? So that we meet on Wednesday, we fully complete the Bayes theorem. Next week, we will look at the unit 2. But next week, we will move a little bit faster. We'll move a little faster so that we can quickly catch up. It seems today, if we go a unit a day, we might not finish. So next week, we will complete both unit 2 and unit 3. We'll complete both unit 2 and unit 3. But Wednesday, God willing, we want to finish the Bayes theorem. And please, do we agree to it? That we meet on Wednesday?
Set time, Wednesday. When?
Okay, Wednesday. I'm looking at Wednesday. Initially, I said 7 to 8, 7 to 9, but I want to move it to Wednesday, 6 to 8 o'clock. 6 to 8 o'clock. Would that be okay?
Yes, that's good.
Yes,
sir.
Yes, it's
I
okay.
agree.
Yes, sir.
Okay. So thank you very much, and please have a good afternoon.
A suggestion.
Sir,
Thank you, sir.
Okay,
can
a
we have
suggestion.
slides?
Yes.
Morning or evening?
Okay, we want to have that in the evening, 6 to 8 in the evening.
Wednesday in the evening.
Yes, Wednesday in the evening. 6 to 8.
Okay.
A suggestion.
Sir, the
Please.
slides.
Yes,
Can we
yes,
have?
Watson.
Can we have it?
I will share the slides. What is Samuel?
Sir,
Yes.
please, I'm pleading. If we can get a pen so that
the writing pen.
Yeah.
Okay. I will work on it.
Okay, thank you. Because some of us we were
Struggling.
dozing. Yeah.
Yeah, I get it.
Yeah. So thank you.
You're welcome.
Hello, sir.
Yes, Gifty.
About the slides, can we have it also that some of us want to print them out? So if you can share everything to us so that we can print them out.
Okay, Gifty. I'll do that.
Thank you, sir.
You're welcome. Okay. So please thank you and have a good evening. Sorry, a good afternoon.
Yeah. Good afternoon,
You're
sir.
welcome.
Doctors, once we upon the when you have to best research. Koda.
Yɛnhyia bie mu no anaa yɛbɛsan ahyia.
Yeah.
Dabi another any class be my senior.
Okay. Romas.
One say. Ubapon.
You see, doctors no Monday and maybe Saturday.
Was it 7 o'clock to 9?
9:30 wa in Fakon.
9:30. Oh, okay. When I'm the 9:30 nation bottle by my yaba 9:30.
Say that, baby.
Next year, 24 people.
Man, man, Sammy,
24 people, 2029.
Joshua Kwana. Say healthy. Only one healthy. Only one equal health.
But doctors, you open papa.
Down.
Healthy. We have heaven our power say health. What is health? Healthy.
Obibeka, we don't understand here. More than day. I should go and back for.